Okay, welcome back. I'm going to call this one Lesson 2 Continued because it's still under the notion of finding limits. The sandwich theorem is often used to help you find a limit. I'll read it first. It says, suppose that g of x is less than or equal to f of x, which is less than or equal to h of x, for all x in some open interval containing c, except possibly at c itself. Suppose also that the limit of g of x and h of x is equal to L. Then basically, then we know that the limit of f of x will also be equal to L. And the easiest way to say that is f of x is being sandwiched in between g of x and h of x, which is a lower and upper bound, basically, on the functional values. And if their limit is L, so too is the limit of f of x. Let's take a look at a drawing that'll help us. Okay? So, in this example, the author wants us to use the sandwich theorem to show that given in this problem, what the author wants us to do, and again I'm copying this from the book, but just to give you an example, given that 1 minus x squared over 4 is less than or equal to u of x, which is less than or equal to 1 plus x squared over 2, the author wants us to, find the limit as x approaches 0. Okay? And no matter how complicated u of x is, so even though we don't know what u of x is, we know something about the sandwich theorem. So find the limit as x approaches 0 of u of x, and I'm just going to say despite how complicated the function may be. Okay, well, let's start off with the drawing. What that basically means is that if you think about what 1 minus x squared over 4 looks like, it's an upside down parabola, right? So you could even throw that in their calculator if you wanted to see, but 1 minus x squared over 4 is an upside down parabola, and 1 plus x squared over 2, I'll do this in another color, and by the way, they both pass through that point, is a parabola, so 1 plus x squared over 2. And what we're saying, we're given that mu of x sort of lives in between there, is sandwiched in between there. So according to, I like to think of it here, so mu of x, all we know is that whatever mu of x is, it lives in between there. So I like to think of it as like this. This is the upper bounding function, so the limit on that is 1. The limit as x approaches 0. And I'm going to write this out a little more formally here. The limit as x approaches 0 of 1 plus x squared over 2 is equal to 1. Even try plugging 0 in there. 0 squared over 2, 0, plus 1 is 1. The limit as x approaches 0 of this lower bounding function, 1 minus x squared over 2, is also 1. And according to the sandwich theorem, since mu of x, despite how complicated it is, as long as it lives in between there, for all x not equal to 1, we're told that it does. If I could look back at the other slide, oops, which I erased, but we are told that mu of x, is sandwiched in between those two functions, 1 minus x squared over 4 and 1 plus x squared over 2, for all x not equal to 0. Then we know that the limit of mu of x is also equal to 1 by the sandwich theorem. So I hope that, so basically the sandwich theorem, I'm going to write it here, then implies that the limit as x approaches 0 of mu of x is also equal to 1. Okay? I'd like to pull up a problem from the online homework. It's also called the sandwich theorem, sometimes called the squeeze theorem or the pinching theorem, depending on your textbook. Let's pull up a problem from the homework. Okay, so here's I pulled up problems from my math lab, or my calculus lab in this case. It might be really small for you to read, so I'm going to rewrite it here. It doesn't blatantly tell us to use the sandwich theorem, but we know we need to. So it says if root 7 minus 5x squared is less than or equal to f of x, I'm rewriting it so you can see it, which is less than or equal to root 7 minus x squared for all x in between -1 and 1, basically. Find the limit. So the author doesn't blatantly tell us what to do. Find the limit as x approaches 0 of f of x. So your trigger is that they're telling us that f of x is sandwiched in between two other functions. It's like a lower bound and an upper bound. Hence the squeezing theorem or the sandwich theorem. So what you would do then, if you're interested in the limit as x approaches 0, investigate that in those lower and upper bounds respectively. So meaning, what's the limit as x approaches 0 of root of 7 minus 5x squared? Well, store 0 in there, you're quickly going to see that's root 7. Okay? Do the same for the upper bound. If you store 0 in for x, 0 squared 0, 7 minus 0 is still 7, also root 7. Now you'll see I already filled in the final answer, root 7. So that's how you get root 7. You basically look at the limit of the upper bound, the limit of the lower bounding function and the upper bounding function, and you know that f of x is sandwiched in between there. So by the sandwich theorem, you know that it will have the same limit, which is root 7. Okay. Hope that helps. Oh, I did want to try one more problem from the homework because we've been working a lot with limit laws and limit rules and finding limits. This is the last problem we'll do for today. Limit as x approaches 0 of f of x equals 3. So first I'm gonna write all the givens in this problem. So the limit as x approaches 0 of f of x, they're telling us, is equal to 3. They're also telling us that the limit as x approaches 0 of g of x is equal to -5. And then it says, name the rule or limit law that is used to accomplish each step of the following calculation. Well, notice it says the limit of 2f of x's minus g of x over the bottom, which is f of x plus 5 to the 1/3 power. First thing they do is they separate it like that. Well, that's the limit of a quotient is the quotient of the limits. Hopefully you're thinking that's the quotient rule. So let's take a look. Quotient rule. Hit check answer. Good job. Okay. Now it's telling us to evaluate the limit of 2f of x minus the limit of g of x. See, it's writing it out. It's expanding it like that. Well, what did it do to the numerator? Well, it used the difference rule. And in the bottom, and in the bottom it used the power rule. The limit of f of x plus 5 raised to the 1/3 power basically took the limit of f of x plus 5 and then eventually raised. So you're using a combination there. You use the difference rule in the numerator, but you use the power rule. Well, you could call it a root rule because it's a cube root. Oops, doesn't like it like that. Let's try that again. Yay. Just treating it as a power. Raising something to the 1/3 power is the same thing as taking the cube root, but it wants you to say power rule there. Okay? And then notice that the limit of 2 times a function, what did they do? They pull the 2 out front. So that's like the limit of a constant times a function is the constant times the limit of the function. So you can see what was used there. We use the constant multiple rule. And downstairs in the denominator, they use the sum rule.